This is an example of calculating the arc length of a curve that is traced out by a vector function. So we're given the vector function r at t, and in order to calculate the arc length, we're going to use the arc length formula, which, as a reminder, is going to be the integral from alpha to beta of the magnitude of the derivative vector function integrated with respect to the parameter. The values alpha and beta are the values of the parameter that start and stop the section of arc that we're trying to measure. And in this particular case, we're not given those values of the parameter. What we're given are ordered triples that start and stop that section of the curve. So the first thing that we need to do is figure out what those limits of integration are. So let's start by copying our position vector function, and I'm going to switch over to pointy bracket notation. And the lower limit of integration alpha is going to be the value which, when plugged into the vector function, yields a vector that terminates at the ordered triple 1, 0, 0. So essentially we need to figure out who is the value of alpha that makes the cosine equal to 1, and when alpha is equal to 0 we have a cosine of 1. So it seems like alpha would be equal to 0 radians. Does alpha is equal to 0 also make the sine value equal to 0? Yes, it does. And would alpha equal to 0 also make the ln of the cosine equal to 0? And we say the ln of the cosine of 0 is 1, and the ln of 1 is equal to 0. So we do see that our lower limit alpha should be 0. Now let's figure out the value of beta that, when plugged into the position vector function, yields a vector that terminates at the ordered triple, rad 2 over 2, rad 2 over 2, and the ln of rad 2 over 2. So we're looking for the value of beta that would be plugged into the position vector function that would cause the cosine to be rad 2 over 2. Seems like our value of beta would be pi over 4. Would pi over 4 plugged into the y component also yield the output rad 2 over 2? Yes, it does. Would pi over 4 plugged into the z component also yield ln rad 2 over 2? Yes, it does. So we've determined that our limits of integration are from 0 to pi over 4. Now, to determine the integrand, we need to find the derivative vector function. The derivative of cosine is minus sine, the derivative of sine is cosine, and the derivative of the ln of cosine by the chain rule is going to be 1 over cosine times the derivative of the inside, which is minus sine t. So that's going to end up making the z component negative tan t. The integrand is going to be the magnitude of this derivative vector, so we're going to square each of these components and add them together. Negative sine t squared is sine squared t positive. Cosine t squared is cos squared t. Plus negative tan t squared is going to be tan squared t. And of course we know sine squared plus cos squared is 1, so this turns out to be the square root of 1 plus tan squared t. So our arc length formula is going to be the integral from 0 to pi over 4, and the argument is 1 plus tan squared t, and we integrate with respect to t. Let's recall from trigonometry that 1 plus tan squared t is equal to the secant squared of t, so we can replace this radicand with secant squared to get the integral from 0 to pi over 4 of the square root of secant squared t dt. Let's also remember that the square root of a variable squared is the absolute value of that variable in order to ensure that we have a positive output from the principal square root. But since we're integrating from t is equal to 0 to t is equal to pi over 4, and the secant of an angle is always positive in that region, so we can actually evaluate rad secant squared to just be the secant of t dt without absolute value bars because of the limits of integration that we're using. Which is good because that makes the integral much easier. The antiderivative of secant is the ln of the absolute value of secant t plus tan t, and then we'll apply the limits of integration from 0 to pi over 4, and this will give us the ln of the absolute value of the secant of pi over 4 plus tan pi over 4 minus the ln of secant 0 plus tangent 0 Let's come back up here to our unit circle to remember that at 0 we have a cosine and sine of 1 and 0. At pi over 4 we have cosine sine rad 2 over 2. And when we look at the secant of pi over 4, which is going to be the reciprocal of the cosine, that's going to end up being just radical 2 after we simplify. Tangent of pi over 4 is 1. Secant of 0 is the reciprocal of the cosine, so that's just going to be 1 as well. And tangent of 0 is going to be sine over cosine, and that's going to be 0. So our arc length turns out to be the ln of, I'm actually also going to drop these absolute value bars because what we have in here is already a positive quantity, so no need to wrap it up in absolute value bars. So I'm just going to change that to brackets, rad 2 plus 1 close bracket, minus basically the ln of 1, and the ln of 1 is 0, so let's just erase that bit so that this would be our final answer.